Welcome to this video on the Compton Effect, a pivotal moment in physics that proved light is made of particles. The image illustrates an incoming photon scattering off a recoil electron, losing energy in the process. Arthur Holly Compton received the Nobel Prize in Physics in 1927 for this discovery, foundational to quantum mechanics. The Compton effect describes what happens when a high-energy X-ray photon collides with a loosely bound electron, much like a billiard ball collision. The photon transfers some energy to the electron, causing it to fly off. Crucially, this energy loss means the scattered photon has a longer wavelength, a phenomenon known as the Compton effect. Comparing the state before and after the collision, we see the change. Before, the electron is at rest, and the photon has a wavelength, lambda 0. After the collision, the scattered photon has a longer wavelength, lambda prime, and less energy. The increase in wavelength, delta lambda, is always positive. The Compton formula precisely describes the wavelength shift. Delta lambda equals the Compton wavelength constant multiplied by 1 minus the cosine of the scattering angle, theta. The shift depends only on fundamental constants, and the scattering angle dictates the magnitude of the shift. At 0 degrees, the photon passes straight through, resulting in no shift. At 90 degrees, the shift is half the maximum. The maximum shift occurs at 180 degrees, a head-on backscatter. Let's apply the formula to solve an example. We want to find the change in wavelength for an X-ray photon scattered at 60 degrees. First, we write the formula. Then, we substitute the known values for the constants and the angle. Finally, calculating the cosine of 60 degrees gives 0.5. The resulting wavelength shift is 1.213 times 10 to the power of minus 12 meters. The Compton effect was revolutionary because it contradicted classical wave theory. Wave theory incorrectly predicted no change in wavelength and failed to explain the energy transfer. Quantum particle theory, by contrast, perfectly matched the experimental results, proving that light consists of particles with energy and momentum. Has many real-world applications. It is used in medical imaging like CT scans and in nuclear radiation detection through Geiger counters. It's also vital in material science, astrophysics, radiation shielding design, and underpins quantum computing. The Compton effect is an X-ray photon scattering off an electron, losing energy and increasing its wavelength. The shift is calculated using Compton's formula and depends only on the scattering angle. This discovery proved the particle nature of light and earned Arthur Compton the Nobel Prize in 1927. Arthur Holly Compton stated that the Compton effect showed the world that light is both a wave and a particle, confirming that nature is quantum. Thank you for learning. Keep questioning and discovering.